In this problem video, we're going to determine the oxidation number for all the atoms in hydrogen peroxide, and also we're going to write a balanced chemical equation for this process, and then identify oxidation numbers for the atoms throughout. I provided the rules that we have in our textbook over on the right-hand side of this page. So go ahead, pause, and try both of those problems, the peroxide and the water electrolysis problem. Okay, let's give it a try. So, if I look over at this set of rules, I don't have the pieces that I need. There's nothing talking about what to do in this case. Yeah, it tells me the whole molecule has to end up being the total charge, which is 0. Hydrogen, I'm expecting to be a +1, but it can also be a -1. So I'm actually going to go ahead and add that a little bit of detail here. Oxygen is usually a -2, but it can be a -1 for peroxides. I'm just going to write it as PO. And that's one that you'll see in some of the other tables that are out there, but it's not on this one, and that's probably a good thing. Now, that's a little bit confusing though, because why isn't it on this table? And simply it's an exception. So when you run into a problem where you couldn't come up with a real answer, notice that here, if it tells me hydrogen is a +1, I'd say that I've got a +1, I've got 2 of them, giving me a total of +2 overall charge. Oxygen, according to this, is going to always be -2. I have 2 of them. That's going to give me, a -4 overall. That means my total charge on this should be a -2, but it's not. So because I know that peroxide can exist, I know that my rules are too incomplete. And that's when you'll really want to use a structural approach. Now, I know it's not ideal that the book's simple approach isn't good enough, but that's just really how it is with oxidation numbers. There's 100 different ways of doing the rules for these, but at the end of the day, if you can't get something that's meaningful out of the rules, switch to the Lewis structure approach, because that's the one that's actually physically meaningful. So, oxygen brings 6 electrons each. I have 12, another 1 and 2. That gives me 14 electrons in the Lewis structure. I have 2, 4, 6, 8, 10, 12, 14. That's going to be my Lewis structure for this molecule. Now, let's make the assumption that it's winner takes all for electronegativity. Now, since these 2 atoms are identical, that means that this bond will be split. There is no winner in that case. So I'm going to go ahead and, for the moment, erase the bond, and I'm going to divvy up those 2 electrons. I can go ahead and look at this one and say, yep, hydrogen won't get any of those. Oxygen is going to get the pair. Now, usually I don't erase it and draw it like this. I actually usually do a tap counting, kind of like I do with formal charge, but I wanted you to see exactly what I'm talking about for it. So right now, hydrogen brought 1 electron with it originally. It currently has 0. That gives hydrogen a +1 charge. Same thing over on this side. We'll be at +1 for its oxidation number as well. Oxygen brought 6 electrons initially. It currently owns 2, 4, 6, and 1 more is 7. It brought 6, it has 7, that gives it a -1 overall charge there and there. +1, -1, -1, +1 does in fact match up to the overall charge of 0, like I'd expect. Now, let me go ahead and show you the exact same thing if I hadn't gotten rid of that set of bonds. What if I leave it looking like this? How can you do that the faster way? Hydrogen is less electronegative. It doesn't get any of the bonding electrons. Hydrogen brought 1, it has 0, it'll be +1. Same thing over here. Oxygen, winner takes all, gets both of the electrons. So it's got 2, 4, 6. I look at this, there is no winner, it gets half, it has 7. Brought 6, has 7, -1 charge. Same thing happens here. You can see how fast that is when you're counting through one of these structures. As long as it's a reasonably simple structure, it's a lot easier to use this than the rules, in my opinion. But sometimes the rules are more useful because the molecules are complicated and you don't have the time to draw them. Now we come down to the second problem. If you haven't done it already, pause the video and give it a try. So water can undergo electrolysis. I just said it went through a reaction, so I'm going to draw my arrow. It can be broken into O2, which we know is a gas, so I'll write it in because why not, and H2 with electricity. The with electricity tells me that, yeah, there's electrons being moved all around in this, so I know that I'm going to be able to have redox reactions pretty easily. That doesn't mean that I'm changing the number of electrons. It just means that I was actually able to change where the electrons are. So it's not a balanced chemical reaction right now. I've got 2 hydrogens and 2 hydrogens, 1 oxygen and 2 oxygens. Everything on this side is even. Let's get this side to all be even as well. I now have 2 oxygens, and that's balanced. I have 4 hydrogens, which is not. I do that. Now I have a balanced chemical equation. What I can do next is I can do the rules for these sides. So I've got H, O, H. Shouldn't need the Lewis structure, but I'll jot it down anyway in case I do. Now, hydrogen is going to be a +1. Let me get rid of these little bits of notes. Hydrogen is most of the time a +1 oxidation state. So I'm going to test that out. This will be a +1, and that'll be a +1. Let's make that look more like an H, then a plus. There we are. And this will also be a plus. Oxygen is typically going to be a -2 oxidation state. The sum has to equal the total charge, which is 0. +1 minus 2 plus 1 is in fact 0. So right, this will be the correct set of oxidation numbers for it. Now, oxygen, gas, is going to be its elemental form. Free elements have an oxidation state of 0. And so its oxidation state should be 0, and so should this one. Now, if you want to see that one at play, O2, that's 6 electrons and 6 more electrons, 12 electrons. 2, 4, 6, 8, 10, 12, full octet, not full octet. There we are. This gets kicked in to make a double bond. Let me just clean this up because it's looking kind of sloppy. There we are. That's more reasonable. So this is oxygen. Because it's completely even for this sharing, we can totally divvy them in half. Oxygen brought 6 electrons. It currently owns 2, 4, 5, 6. Brought 6, has 6. No change, 0 charge. Exactly the same logic happens for hydrogen. And so you can see that either of the 2 approaches that we use, the graphic or the rules-based, give us the same answers for all of these ones down below. And when the rules fail us, we can always do the Lewis structure to find out what the oxidation number should be.